I just wanted to welcome everybody absolutely from the bottom of my heart to our new research seminar series. I'm so excited about this new series of teaching programming with or without AI. I think this is going to be a really big thing for us all to consider in the computing field as to how we use generative AI and other similar kind of technologies over the next few years. So I'm thrilled to be able to kind of say we've got Dr. Barbara Ericson and Xinying Hou with us today, who are from the University of Michigan, which I'm sure it's really cold there right now. So Barbara is a professor in the School of Information, and her research interests include computing. Oh, I know, it's a great long list. Computing education, learning analytics, artificial experience, user experience. And also I know it's so much about, it is a CS education and Parsons problems that I always associate with Barbara. So Barbara creates and studies ebooks, the amazing Runestone products, and she won the 2022 CIGSE Award for Outstanding Contributions to CS Education, and absolutely rightly so. And Xinying Hou is a third-year PhD student who focuses on innovative learning technologies to support programming education. And don't we need that help? And she's currently investigating the use of generative AI to provide engaging and comprehensive scaffolding for our novice programmers, and they definitely need that help. And in their presentation today, Barbara and Xinying, they're going to explore this use of generative AI to create personalised Parsons problems. And as all of you know, all computing educators know, learning about the syntax of programming language is very difficult for many students. And whilst Parsons problems help students to start to decipher that code structure, teachers can often find it challenging to precisely identify and address students' misunderstandings. And we're really excited to hear about this new approach presented by our speakers today, who've researched how to kind of provide personalized solutions to bridge these gaps. So hopefully I've kind of described that correctly, but we're going to find out now. So I'm going to pass over to Barbara, who I think is going to start, and we'll see how it all unfolds. So off you go.
All righty, thank you, Jane. And I put a link to the slides, and I think Bonnie is going to do that as well. So let's move on. So I first want to just explain a little bit of my background. So I got both a bachelor's and master's in computer science, and I worked at a bunch of companies, but I was also the director of outreach for Georgia Tech. And I did a lot of teacher professional development. I created curriculum. We were writing books. So that's sort of my history. We were also working with kids. We were running summer camps and weekend workshops. I used to joke that I got people to pay me to experiment on their children. And then I decided I should learn what I'm doing. I don't really know research. So I decided to get my PhD. So I started my PhD in 2012 at age 50 and finished in 2018 in human-centered computing. And now I'm a professor at the University of Michigan. And the areas I'm focusing on, in particular, are active learning. So we know that people learn better if they're active than passive. And particularly, I'm looking at interactive ebooks, Parsons problems, as Jane said, and I'll explain what those are in a moment. Peer instruction, we'll explain that too, and POGL. And then I have some PhD students that are focusing on social justice. I've also been running near-peer mentoring programs, particularly for secondary students to help them succeed. In the US, we have something called advanced placement that secondary students can take for college credit or placement. So I run programs for that. And then I've developed curriculum. One of the things my husband and I are known for is media computation, which is an approach to teaching computing by having students write code that manipulates media, like pictures, sounds, movie frames. And I've also created an online course that I'll talk about. So active learning, often this is based on ICAP framework from Mickey Chi and Ruth Weil that says that interactive is better than constructive, is better than active, which is better than passive as far as learning goes. And interactive, you can think of things like elbow partners, or think pair share, right? Talking with people around you, peer discussion. Construction is creating something new, like writing things in your own words if you're taking notes. Active is just being active, moving something. Passive is a typical lecture where not much is happening. The students are not engaged, at least cognitively. So cognitive load theory is one of the things we're drawing on that says that all learning occurs in working memory, which is limited. So, so many can only hold so many things at a time, but you can do more if you can chunk things, if you can take large things and chunk them, like learning a song or learning dance. If you say, okay, I'm going to do the Macarena. Well, once you know that, you're just like, oh yeah, da, 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 da. You understand all the pieces, you put them together as a chunk. So for learning to occur, you have to process things in working memory with limited capacity, and then it moves into long-term memory. So one of the things that from that theory is that completion tasks are easier on people than hold tasks. And we know that people often, if you ask them to write code from scratch, that's a hold task, and that can be overwhelming. So giving them a completion task is much easier on them, lowers the cognitive load. And it is affected by how much prior knowledge you have. So it does predict effects like the worked example effect. And research from educational psychology shows that giving people worked examples plus interleave practice, so here's some example code that's explained, plus practice to get you to pay attention to that code and use it, is best. So that's kind of the things I was studying during my PhD. And one of the things we started doing is creating free and interactive ebooks that are based on those educational psychology principles. So worked examples plus practice. We've also created timed exams. The advanced placement computer science courses have a timed exam at the end, and those are very useful. I use them all the time for my class now, so I'm going to show you just that. One of the PhD students here created a space practice tool. We know that space practice, where you practice over time, is better for long-term retention than cramming, like the night before an exam. You may remember it for the exam, but you're going to forget it immediately after that. So, but often space practice students don't want to do space practice. So he created a tool that's integrated into the free ebook platform Runestone that encourages people to do space practice. And then, of course, lower cognitive load problems like Parsons problems that are a completion problem. And then I've been creating ebooks, and the two that I most have users for is CS Awesome, which was created for advanced placement computer science A course, which is equivalent to a college level CS1 in Java, object-oriented programming in Java. And then the course that I teach at Michigan is, I use this Python for Everybody interactive course that's Python. And you can see an example here of a worked example plus practice approach. Here is working code to get it create a turtle object, have it draw this picture, and then we'll add practice, like multiple choice questions or Parsons problems that get you to pay attention to that, like which way does a turtle move when it's first created? Well, since it's drawing that way first, it would be going east. So you could pick east, check, get result. So Runestone Academy, which is the open source ebook platform that we use, was first created or founded by Brad Miller, who was a professor at Luther College. And he wants to democratize textbook. He wants everybody to be able to learn from a free textbook, not have to pay hundreds of dollars for a textbook. Currently, there's over 30 free books, both computing and math there, and there's a URL and a QR code if you want to take a look at some of those books. And then timed exams, this is what a timed exam looks like. Instructors can create custom courses from any existing course in the ebooks, and then they can create assignments for their students, including exams or timed exams. And in a timed exam, the students will have a certain amount of time to finish, and you can assemble it with multiple choice questions, fill in the blank questions, Parsons problems, write code problems that have unit tests, and they can compile code. They don't see the results of the unit tests, but they can compile the code. You can give them some example code that with input output to make sure that those are working correctly. And they don't get feedback on their exam during the exam, right? They have to just try. The space practice tool, what that does is display previous questions from the ebook based on what the users covered already. So what pages have they visited? Uses an algorithm to predict what they're likely to forget. It also looks at how well they performed on questions from a particular topic. So it brings back topics that they haven't done well on until they're doing well on them. They earn, as an instructor, I can set the tool up to have them earn X number of points over Y number of days in a semester to encourage them to practice over the semester. And then when they're answering a question, it'll show them some question. They can say, done, ask me another. Or if they get a question that they don't really know the answer to, they can say, I want to postpone this to tomorrow. And then hopefully they look up, what is that thing? So We have found that students mostly like this tool. They really enjoy it gives them fireworks when they complete the points for the day. And each hour of using the practice tool was associated with a 1% increase in the final exam grade. So what's a Parsons problem? It's an example of a completion problem where you're given all the correct code to solve a problem, but it's mixed up and you have to put the blocks in order. And so usually, as you see here, you'll have mixed up code on the left and you'll assemble it into the correct order on the right with the correct indentation, since this is Python and Python requires indentation. Plus indentation is a useful thing anyway. You can have distractor blocks. You'll notice this 1A, 1B print greeting. The only difference is the missing parentheses on the 1A. And those are pairs of correct and incorrect code or distractor code, which often are common syntax or semantic errors. And you can either require indentation or not. And these were first named for Dale Parsons, and she and Patricia Hayden wrote the first paper in 2006 about this. So some of the prior research on Parsons problem that I learned from when I was starting my PhD was that there was some things known about them. We knew that most students thought they were useful, that distractors increase the difficulty of the problem. But if you pair the correct and incorrect distractor blocks, that's better than randomly mix the distractors in. That's easier on people. Providing indentation reduces the difficulty, and less blocks versus more blocks reduces the difficulty. So some of the things I've researched, or my team's researched over the years, is I first put them in an ebook, and pretty easy ones, and then check to see, did anybody try these? Yes, I had them in a free ebook. We had people use the free ebook, and then I looked at the log file and said, oh, good, people actually are trying these. Yay. And most people were getting them correct in 1 or 2 attempts, which is what Dale Parsons had originally said was the goal, is get them correct in a couple of attempts. However, we found that some people really struggled and some never solved them. And of course, we know that if you're not successful at practice, you're not going to learn. So you have to be successful to learn. So I wanted to figure out a way to make people more successful. I did some randomized controlled experiments of solving Parsons problems versus fixing the equivalent code versus writing the equivalent code. And we found that there were equivalent learning gains from pre-test to post-test. There were learning gains and they were equivalent, but the students were significantly faster at the Parsons problems than either fixing or writing code. They were actually the worst at fixing code, which is not surprising with beginning students. We also found from looking at log file analysis of both adaptive and non-adaptive Parsons problems that people were nearly twice as likely to correctly solve the adaptive. And I'll explain what I mean by adaptive in a moment. And most people prefer the adaptive. We also find from end of course surveys with my students, as well as other researchers have reported that most students, 75% and up, find them useful for learning programming. However, there are students who would rather write the equivalent code than solve Parsons problems. And that's consistent with cognitive load theory that says that there's expertise reversal effect, that things that we do to help beginners often can impede experts. And so as scaffolding is intended to help people that are struggling. You want scaffolding to fade as people develop expertise. We also found that Parsons problems are not faster to solve if the solution is unusual or different than what the student was trying to do, right? Then the cognitive load is increased. So what are adaptive Parsons problems? There's 2 types that I created. One is the same problem adaptation or intra-problem adaptation. And if the user is struggling to solve the problem, so for example, here, trying to use a turtle to draw a triangle, putting code here on the right side, once they create a complete solution, they can check their result. There's a little check button at the bottom. It'll highlight any blocks that are in the wrong place or the wrong blocks that need to be moved. If you have at least 3 attempts to solve it and you're still wrong, then it popped up saying you can use the help button. First thing it said is it was going to get rid of an incorrect block. So the distractor moved over, which is that big hint to use and repaired with the correct block, which was a big hint to use that one. If you still need help, it'll start combining blocks using the ones that are furthest apart. And it'll do that until it gets down to 3 blocks, and it'll tell you, hey, 3 blocks, you should be able to put that in order. And in this case, it was in the correct order, but some indentation still had to be done. And then it shows a different arrow to show you, hey, you have to indent that yet. The other thing we did was, oops, sorry, next. inter-problem or different problem adaptation is based on how you did on the last problem will modify the difficulty of the next problem. So if you solve that last problem in one attempt, you found it very easy, well, then we try to make the next one harder by not showing distractors paired and using all the distractors. So just randomly mixing in the distractors. And otherwise, though, if you struggled on the last problem, we try to make the next problem easier. So remove some of the distractors, pair the rest with the correct code. One of the things we also ran into from our research was because some people would rather write the equivalent code and scaffolding should fade as people develop expertise, is we created toggle problems, where given the mixed up code problem or the Parsons problem, we add this toggle that says, hey, if you'd rather solve the equivalent write code, go ahead and toggle to it, switch to it. And so it'll take its place in the ebook and go ahead and write the code for that. You can toggle back and forth. We grade whatever one you leave in the book. So we've given an option for you to get rid of the scaffolding if you don't think you need it. We've also created new kinds of Parsons problems called micro-Parsons problems for both regular expressions or regex and SQL, which is structured query language. And they're most typical Parsons problems. You have one or more line of code and blocks that you're putting in order. In a micro-Parsons problem, we're creating a simple singular statement, so a single line of code. Or in this case, regex is this very terse language of symbols. So this is saying if I want to match create a regex that matches both cat and cats, well, that means I want to match cat with the S being optional, and the question mark means optional. And it would highlight if you had wrong blocks, use the distractor block. We could also use SQL queries. We can create SQL queries like create table here. So this is work of another of my PhD students, Xinying Hou, and so far what she's found is that we did between subject study, and several different studies actually is what we're talking about here. One of them, she had micro-Parsons as optional practice in a MOOC, and she had thousands of students who started the practice. Very interestingly, students who were in the Parsons condition versus the normal text entry condition for regex, we lost a lot more people out of the regex condition. They just quit. This is too hard. We're done. Whereas we kept a lot more people in the Parsons condition. So we had a significantly higher completion rate with micro-Parsons than with text entry, which gives you evidence that they found micro-Parsons much easier than the text entry. We also had higher learning gains on meaning of certain regex symbols. She also tested two types of feedback with SQL. There's two kinds of possible feedback with Parsons problems. One is block-based, which I showed you, that highlights blocks that are in the wrong place. Another is execution-based, just give you the compile error or the runtime of something. So she tested both of those, and she found that students who solved SQL micro-Parsons in the block-based condition, block-based feedback, had significantly higher learning gains. And that's not surprising because we know that students don't understand compiler errors or feedback. It's in line with my fixed code research. And then the other thing we decided to do was, okay, if we can pop up, if we have Parsons problem, we can pop up the write code and you can switch to that. Well, why don't we do the opposite too? Why don't we use Parsons problem to scaffold students while they're writing code? So they still have to solve the write code problem, but we give them that option of popping up the Parsons. They can even solve the Parsons problem. Currently in the ebook, they still have to write the code over in the write code area to get the credit. They can't just copy the solution from the Parsons problem. And then that brings us to Xinying's work. So I'm going to let her take over for the moment.
And so I'll now dive into the use of Parsons problems to support the co-writing, and how we recently started to leverage the power of AI to generate multi-stage personalized Parsons problem as a co-writing support. So in the very first study on this direction, we look into a more comprehensive support method by providing the equivalent adaptive Parsons problem for a write code problem. So the solution we put into these Parsons problems is from a common student solution from previous semesters, which means like all the students received a Parsons problem with the same student solution. So we hypothesized that the Parsons problems will be useful in supporting students because they let students apply problem-solving skills while limiting the irrelevant cognitive load and keep students engaged in learning. So we hear some good results from students. So students found Parsons' problem helpful in supporting them in completing the right code problems. And 6 students stated that the Parsons problem aided them in lower the difficulty of the problem, speeding up the problem-solving process, and also reducing their debugging time. Also, most students found Parsons problem helpful in getting a clearly understanding of how to create a correct solution. And also, given that the solved Parson solution contains current information about programming language syntax and semantics, students mentioned that they clarify their misunderstandings and learn new syntax by using the Parsons problems during the co-writing practice. And additionally, students also found Parsons problem prompt them to think more deeply. So one student compared it directly with providing an answer and claimed that the process of solving Parsons problems made them think. So while the Parsons problem provided a wide range of help, some participants encountered challenges during this process. So one challenge that inspired our follow-up work is that students have difficulty in solving the Parsons problem we provided as support. So given that in this version, we use only one common student solution to create the Parsons problems. So students who had a different approach in mind might experience a higher cognitive load and did not find this Parsons problem as support useful. For example, one student said, I was thinking differently on how to approach it. So it's just a Parsons problem did not seem reasonable to me. So also 3 students experienced their dissatisfaction with the use of distractors during the practice. So they found showing distractors sometimes hindered their ability to process through the questions more smoothly. Also, because this distractors was created by the experts, so sometimes it did not always align with the students' own thought process, leading them to deviate from the correct answers more easily. So we were thinking can Parson support align with the student's approach? And also can Parson support provide more targeted distractors rather than the distractors provided by the experts? So after this study, we also wanted to explore how this supporting method can specifically help students with lower self-efficacy. So students with lower self-efficacy in computer science learning generally feel insecure about attempting the computer programming problems, doubt their ability to learn programming and handle difficult programming problems. And they also have less confidence in achieving good grades in computer science. And these students are less likely to persevere when faced with difficulties and more likely to drop out from the intro level computer science classrooms. So we ran a between subject study for students. One group has a Parson support when writing the code, when finishing the write code practice, and the other one has to write the code independently. So we discovered that students who had lower self-efficacy levels in computer science show significantly higher performance in write code practice and problem-solving efficiency when they received a Parsons problem as support during their practice sessions, compared to those who had to write code independently. As for how the students with varying self-efficacy levels use the Parsons problem as a write code support, we observed that the students with lower self-efficacy were more likely to solve Parsons problems during practice. So it acted as a helpful tool for them to solve the problems. And these findings provide evidence that Parsons problem can create a more supportive learning environment, particularly for students with lower self-efficacy and had difficulty in solving the write code problems. So this enables them to engage in a more meaningful write code practice as a part of their learning process. Conversely, students with higher self-efficacy tended to use the support in a more lightweight way. For example, maybe they just scan the Parsons blocks without solving it, or they just do a little bit drag and drop. So, or they even choose to solve problems independently. So this, of course, indicates their confidence in their abilities and leading them to seek less external assistance. So this made us think that in this case, maybe providing a fully movable Parsons problem as support might redundant to them. So alternatively, they might benefit from a more concise support as needed, which align with their preference for more self-contained problem solving. So these studies were conducted before the availability of ChatGPT. As you may be aware, generative AI tools have gained increasing popularity over the past 2 years. And some notable commercial products include like GPT Copilot, OpenAI ChatGPT, and Google Bard, and more and more. So these tools are powerful and can accomplish a wide range of tasks. And one of the most notable abilities of these generative AI tools for us is their ability to generate relevant code based on the natural language input. So for example, these tools can just generate the code that meets a specified requirement when giving a natural language description of the desired functionality. So this is similar to the format of many CS1 write code problems. So these tools are widespread and easily accessible. So when students do not know how to solve for example, the write code problem here, they can just like simply throw it the problem specification into ChatGPT, get the complete answer in 3 seconds, and submit their homework without even like needing to read the solution because they have the copy code over here. So this raises concerns about like the over-reliance on AI without any learning. And also the AI systems can produce like unexpected errors due to their imperfections. So these biases and mistakes in AI can also cause students to over-rely on AI system in an like even more negative way. So for example, this can lead to the learning of incorrect information as they provide seemingly correct answers and that are actually incorrect. So how can we leverage the large language models and AI to support students in code writing practice without hindering their learning? So how can we provide support in a more like engaging way and help students get the correct answer? So in 2023, we designed and developed the code Tailor, which is a system I show here. This is the main interface of the system. So code Tailor is a system that tries to deliver real-time, on-demand, and multi-stage personalized Parsons problems to support students while writing code. So code Tailor distinguishes itself from like existing large language model-based products by emphasizing an active learning opportunity where the students are expected to solve the problem in the support rather than simply acting as customers of the presented correct solution. So here I use 3 hypothetical student scenarios to demonstrate how the code tailors personalization design in more detail. So for example, this is the first scenario. Imagine that Rita is a beginner Python programmer who learns Python for like 2 weeks. After like getting some basic concepts, she started to practice her coding skill with a code tailor. And she attempts to write a line of code to solve this problem, but encounters a problem and then asks for support. Since Rita is still in the very early stage of the problem solving and has not contributed much in the code writing section, code tailor presents a fully movable person's problem without any distractor blocks. And Rita attempts to solve it, but continues to struggle even after like 4 tries. So she then can combine the blocks into one and complete the remaining arrangements independently. So finally, she enters the solution into the record box and passes out the unit test. So the second scenario is receive a partially movable person's problem with paired distractors from student errors. For example, a student Molly, she successfully completed an intro-level Python course 3 months ago and is now like trying to pursue her skills through like practice and review with code tailor. So whenever she encounters challenge with her written code, code tailor is here to provide support to get her success. So to help Molly, code tailor provides a partially movable person's problem where the correct lines are static blocks and the remaining lines can be rearranged to fix any errors. So furthermore, the code tailor also generates targeted distractors using Molly's own error lines. For example, those are the 2 lines Molly did wrong, and the code tailor used these incorrect lines to create the peer distractors and pair them with the correct line in the solution. So when Molly sees the distractor, she realized that, oh, she forgot to include a colon in the particular line, like the third line. So with this insight, Molly successfully completes the person's problem, copies the solution, and confidently submits it, passing out the unit test. So the third scenario is receive a partially movable person's problem with paired distractors from both AI and student errors. So for example, Luna has been using Python for like 6 months and practice with Tailor to prepare for more advanced courses. So when Luna encounters errors after believing she has finished a problem, she asks Tailor for help. Yes, Tailor is still here, and Tailor provides a partially movable person's problem with a fixed solution to assist Luna with her buggy code. So since Luna's code only has errors in one line, Tailor generates a distractor set based on her own error and also converts one key line, for example, the line 6. This is a key correct line into a movable line with a logical error provided as a distractor block. So Luna compares the large language model generated distractor with the other paired block to reinforcement her understanding of how to do it. And she then completes the person's problem, modifies her own code, and successfully passes all the unit tests. So besides the main personalization mechanism, here are also several features I would like to highlight in Tailor. So in Tailor, when students receive a partially movable person's puzzle, blocks from the student's correct lines are already placed in the solution area, like showing with a dark green background, and are static, like shown here. So built on these static blocks, Tailor gives instructions within white areas, like shown here, at the top and bottom of the static blocks to indicate how many blocks are required in between. So the students can also hover over on a static block to check the number of blocks missing above and below it in the corresponding location. So also when solving the Tailor's personalized person's puzzles, students can use a check button to check the answers and receive timely block-based feedback like this. So the incorrect block is highlighted in red, for example. And also students can also regenerate a new personalized person's puzzle at any point they want. So this gives students more control when they are like unsatisfied with a current person's problem and support, or like when they when they need updated support after changing their own code. So we conduct our first 2 studies in the summer of 2023 to evaluate Tailor from the perspective of the material delivery and student users. So these studies involved 800 formal student buggy code and also 18 novice programmer learners. So through these evaluations, we aim to understand like whether Tailor can provide high quality personalized person's puzzles, and whether the Tailor can offer a more engaging and educational write code experience compared to write code with a typical AI-generated solution. So through our evaluation, we found Tailor successfully generates correct solution from incorrect student code without introducing any errors. And this ability is crucial as it ensures that the correct code remains free from the when students are interacting with AI. And also we found the generative solutions closely align with the incorrect student code compared to a common student solution from previous semesters. And in addition, compared to the traditional fully movable person's problems, Tailor also provides a person's problem that are more concise by reducing the number of blocks students need to consider when solving it. For example, we pre-placed some of the blocks the students got it correct. So this can provide a more focused and efficient learning experience, especially for students who only did 1 or 2 lines wrong. And in addition, in the study with 18 undergrad students, when comparing the use of Tailor to a typical AI-generated solution, students found Tailor more engaging than receiving the code directly, and like they reported significantly higher engagement due to comparing to this baseline support. So such high engagement comes from like the interactive block manipulation. So for example, one student mentioned feeling engaged by the interaction as I feel engaged because I get to move things around and then I get the correct answer. And similarly, another student highlighted the engagement as I feel really engaged because the drag and drop was asking me to do some stuff. And also students appreciate the visualizing the problem as I could visualize where all the different parts of the problems are going to do, and it made me think more about the problem. And conversely, the participants also report like they feel disengaged by using this baseline support. For example, one student said like express the desire for more engaging support, as this could like there definitely could be something like more engaging than just reading the code. So we also found when using the code Tailor, students also recalled and applied more new components to ask the post-test comparing to the baseline support. For example, one student, upon encountering an incorrect syntax in code Tailor, she reflected that I'm trying to remember if that's the way you do length. I think this might be the right one. And then in the post-test, she corrected her misconception after using the code Tailor and applied what she learned from it to the post-test. So we also found 88% of the students prefer code Tailor as support for the purpose of learning through code writing. So most participants share that they prefer code Tailor because it is more interactive and allows them to invest the right amount of effort to achieve the solution. And code Tailor has already completed some work for the learners, such as limiting the solution to the blocks and pre-placing the correct lines, but still allows learners enough freedom to explore. So for example, one student mentioned that it is not exactly like just giving you the answer key, it's still having you to do a bit of work on your part to figure out like what you should be doing correctly. And I think that's helpful for learning. And also participants point out that code Tailor helps them think better about how to build up a solution comparing to just showing them the final correct solution result, such as it can help them to visualize the relationships between different blocks of code more easily. In addition, since the correct solution used in code Tailor is generated based on the student's existing strategy, and it boosted the learner's confidence in their current ideas and progress during the practice. For instance, upon seeing the code Tailor confirm the correctness of 2 lines by put them as static blocks. So one student expressed as I basically sort of did that piece correct, which actually feels great to me. And additionally, the customized destructor blocks from student own airlines aid in like help them to diagnosing their original thinking. So this process further deepens the understanding of their details within the code. So one student saying like by comparing the differences of the destructor blocks with the other block, it allows you to understand how different pieces of code are important, or like what small changes can actually do to the solution. So however, some students reported challenges on solution comprehension. So one reason is that the code Tailor lacks sufficient explanation to facilitate student understanding of the difficult details. So thanks to the origin block activity in code Tailor, students can understand the overall structure and the main logic of a solution actively. However, like some students had difficulty in comprehending the details within the individual blocks, which prevented them from successfully transferring what they learned from code Tailor to post-test. So textual explanations could help students understand the program's components, objectives, and structure. So they can also help beginners in learning more from the person's problem, like providing an additional opportunity to read the code blocks, understand the problem, and also comprehend the solution. So hence, in our next study, we propose a design to incorporate multiple levels of natural language explanation into code Tailor. So 4 types of explanation will be generated and inserted in real time, enabling code Tailor to provide personalized explanations accompanying the person's problem. So the first one is a sub-goal guidance explanation. So this is gonna present it in the numbered bullet points, breaking down the current programming task into 4 to 6 more manageable task sub-goals. So the sub-goal guidance aims to help students gain a high-level abstract understanding. So the second one is a block level code explanation. So after solving the person's problem and support, students can hover over each block to get an explanation of each block. So these explanations clarify the behavior and the purpose of the person's solution at the block level. And for the paired distractors, the explanation also provides reasoning of why the correct block is right and why the corresponding distractor block is incorrect. The third one is atom level code explanation. So for each block in the person's solution, students can click on an atom which is the individual elements of the programming language, such as the keywords and statements within the code block, to receive an explanation of this on this text surface, execution, and the purpose. And the final one is a self-explanation question to reflect on the person solution. So after getting the right code problem correct, this person solution will appear again without any textual explanations. So this time, students need to explain the reasoning behind the solution in a manual-based self-explanation prompt. So this prompt is designed to minimizing the guessing and enhancing students' understanding to the person solution. So in this case, the large language model will generate the main structure of this explanation like this, and leaving the keywords to be filled in by the student.
So one of the things I also mentioned is peer instruction. And this is one of the things we have the most evidence for, decades of evidence. It was originally created by Eric Mazer. And what he does is he displays a hard multiple choice question that people often get wrong. They often have misconceptions about, like, what is the remainder after 3 is divided by 4? And students will vote individually to answer that, often with like clicker devices, or you can use an ebook. And they can then usually discuss with the people around them, and then they answer again. And usually the vote number, the percent of people that are correct goes up from that first vote to second vote. It's a lot like think, pair, share. More students succeed, but the clickers were really annoying. And so we decided to just add it to the ebook. So we've added support for peer instruction directly in the Runestone ebooks. We also added a couple of new interfaces. One is, during COVID, we had to go remote, use Zoom. It was really hard to do peer instruction then. So what we added was a text chat so that people are randomly assigned to other people who have, in order to maximize the number of groups that have different answers, because most of the learning happens when people discuss their different answers. And so we added that. And then we also added, as if you miss lecture, we have sort of a pseudo text chat where you are served what was somebody else's discussion. Now we're thinking in the future, we're likely to just be getting a new grant that will let us use ChatGPT to try to make that interactive, even if you're answering asynchronously. So we're excited about that. Our research there has found that we get a better learning gain when we do use the text chat, because we can assign people to different groups and maximize the number of groups that do have different answers. We've also been doing POGIL, if people are familiar with that. That's a mouthful. That means process-oriented guided inquiry learning. Or in other words, you're trying to get people to learn what you want them to do by giving them carefully created activities rather than just tell them in lecture. So I've done that in the ebook, and there's a link there to one of them in Python, where instead of me lecturing, I create carefully crafted activities for them to learn what I want them to learn. They can record what they wanted that they learned and what they have any questions on in a Padlet, which is another tool, free tool that you can use to have people anonymously ask questions. And then I go over the questions during lecture. There's a lot of research that shows POGIL increases engagement and grades. This is another of my PhD students, Athars, who's been very interested in social justice and computing. And he's modified some of my assignments to have a social justice slant. And what he's found is that with small, semi-structured interviews with some students, a lot of them say they don't really see that computer science helps people. It's not very, that's not the impression they're getting in a lot of their courses, but it can be used for that. A lot of the students said that they wanted more work with social justice context in computing. And one of the things he's done also in a summer camp is use satirical programming, which is, let's write programs that make fun of some of the biases that happen to expose people to some of the things that happen. Like, for example, Athars, anytime he types his name into a Word document thing, it'll try to correct the spelling of his name. So, of course, these things have been trained on more Western names. His name gets changed all the time. Or when he tries to use devices that automatically turn on water or turn on air to dry your hands, they don't work because he's dark-skinned, and they weren't intended for people with dark skin. So he's using satirical programming to point out where some of these biases or flaws are. Other thing that I've created that some of your people that are here might be interested in is I created a MOOC a while ago on FutureLearn, which is more of a UK platform for online courses. Unfortunately, they decided to move from FutureLearn to Coursera. So they're moving the course. It'll be available again in late February, but it was on FutureLearn for several years. And the audience for this is, teachers. I really created this for teachers to help them get comfortable in Python if they weren't familiar with a textual programming language. Also students, conversational programmers, which are programmers who want to be able to talk about programming, but don't expect to be programmers. So they don't want to learn every detail of a programming language. They just want to learn in general how they can do stuff that's useful. And it's not lecture. It's very much with what I've been telling you about. It's open-ended creative assignments. It's work in the interactive ebook. It's trying to encourage them to work in groups and give each other feedback. So that should be available in late February. So in summary, again, there's the link to the slides. There's the QR code for the RuneStone ebooks. I recommend using active learning, and there's many different things you can do, like the free and interactive ebooks for peer instruction or low cognitive load practice, like Parsons problems. There are several commercial platforms that now support Parsons problems, as well as like Prairie Learn, which is a big homework system, has a lot of Parsons problems. Some people asked in the chat about other language. Yeah, you can do Parsons in any language you want, including English. Doesn't have to be, code. And then with AI, we really should provide guardrails so that students don't get hallucinated or incorrect things. And we do see a lot of potential in using AI to generate or personalize problems or add interactivity. And you might want to incorporate social justice in computing.
That's absolutely wonderful. Can we just give a quick clap for because it's just absolutely wonderful.